switch to English, sorry. Okay, so let's continue our discussion about standard model effective theory. So just to recap, basically we have seen this so the standard model effective theory basically is something that we discussed that whatever is the high energy theory, what we need to describe the current data, still we will see the next particle is something like this. So it's an effective Lagrangian where we have the dimension 4 part, which is what we usually call the standard model, and then with this tower of effective operator, which is nothing but describing contact interaction between the standard model particles if you don't have the energy to excite them. And so let's now just recap. So now we take all this Lagrangian and we can look at operator by operator somehow the property. So we've seen that there is, we look at equal two terms, so which are here. So there is only one operator, dimension 2, which is this Higgs master. Okay. We discussed yesterday, and from this operator we deduce that there has to be a cutoff scale not too far from the TV scale. This was the hierarchy argument I tried to give you yesterday. And this is a very vague statement, but I think it's important. And also it's a statement that there has to be something to screen the Higgs potential, because this term is quadratically sensitive to the cutoff. I don't know what it is, and doesn't need to be the only scale. For sure, we have seen other things that indicate a very different scale, but I think I'm convinced that if there is no, I think this is a quantum field theory statement. If there is nothing that goes beyond quantum field theory, like cosmological evolution that somehow explain this, you just stick to the realm of quantum field theory. High energy degrees of freedom coupled to the Higgs will destabilize it. Therefore, there has to be something not far from TV to stabilize the Higgs. Then at d equals 3, there is nothing. Okay, gauge symmetries forbid any d equals 3 operator. D equals 4 are all the other operators of the standard model, which are 8 and 8, magnetic part, and then color. And these are, they don't tell us too much, okay, and I call it stable and log running. But as we discussed yesterday, very important, the Yukawa coupling is very important because break a lot of accidental symmetries which are there from the rest of the Lagrange. And then what you also seen yesterday, that there is at p equals 5, there is this unique operator, right, like this. Which is the whole Weinberg operator. Which can explain the zero masses. And if we take it at face value, the scale can be very heavy. Or maybe they stated that if coupling is of order 1, then this boundary new is and however, as we discussed yesterday, this is special. This operator is special because violate Lepton number, which which is an exact symmetry of the Lagrange. So it is perfectly conceivable that there are different layers. The layer where we violate L is phi, and so it's a kind of separate sector of it. So what's next? What's next is what happens when we go beyond dimension 5, and we can try to classify all the possible operators. Okay, so this is an exercise which has been done. Actually, it's been done for the first time in the late 80s, and finally, complete basis, now people call it the SMEF basis, has been written down only in 2010. And so I think it's an interesting exercise to see how we can build this operator using the fact that we have to respect as you click all the time, as you do. So we have to respect this symmetry. These are the rule of the game, and we can use as field the standard model field, which are left, right, right. The gauge field, also generically like this, and then these are our ingredients. We want to combine in a possible way, in a gauge invariant way, and build operators. So let me just give you a glimpse of how this works. So for instance, if I take phi only operators, it's clear that you want to have something which is invariant, and to left phi is a doublet. So the operator you can build are objects of this type. Okay, or object that contains the derivative. You also want to respect, of course, Lorentz invariance, so it will be something like this. Then it's clear that here the counting is always, the number of phi is always even, okay? So the dimension starts at 6, so there is not a dimension 5. I want to convince you that actually this is the only dimension 5. Okay? And then we can continue. For instance, if we go to terms with the a mu only, then you have to do something which is gauge invariant. So the gauge invariant object is f mu nu, okay? That you can build with a different with the appropriate term, and so will be object. Okay, this is the kinetic term, and then so more generally you can put derivative on this, or you can put 3 of them with an epsilon tensor. So, but it's clear that we will have something. Let me do it generically like this. Will be again f to some power n with derivative, and the derivative should always be 2 of them, because otherwise you violate Lorentz invariance. So again, dimension more than 6, because f carries dimension 2. Okay.
And third derivative for derivatives.
You can put 2 derivatives, and you cannot put a single derivative, because
single no, but d mu, d mu, d mu, d mu.
Yeah, that's you can do. Yeah, this sorry, the 2 times k. Yeah, always.
It's unlikely that that k is 5 and n is 6, but your analysis there possible.
Yeah, absolutely. But the point is there is not a dimension 5. That is the thing. And then we continue the counting. For instance, psi only. This is very simple. Psi is a fermion. Therefore, if you want to do a Lorentz invariant object, you will have always combination of this type. Psi by psi, you have to contract the spinor index. Okay, so this is dimension 3. Then this will come with some power, and so this is 3, 6, and so on. So this is again dimension 6, fermion operator, and so on. And then you can play the game of putting more things together. Okay, you can put, for instance, psi and a, which is psi and a. Okay, you can see maybe you can do something like this: psi bar L equal to mu psi r f mu. This is fine as far as Lorentz, because this is, and is apparently dimension 5, because yeah, this is dimension 3, this is dimension 2, right? It also respects Lorentz because you knew that the contract index. However, this violates SU2 left because this is left and this is right. So you have to put a Higgs field to compensate this. So again, you go to dimension. Okay. And then you can continue the exercise and you can convince the only dimension phi is this term here. The only dimension phi comes from psi and phi, and we have this Weinberg operator. This exercise was done by Weinberg, who demonstrated that the only dimension phi term is that, and all the rest is at this dimension. Now counting how many operators we have. Okay, so this is just then you have to do the exercise precisely, combining all the things. Let me just give you the result, okay? Because this is instructive. Also, if you go to a seminar nowadays, always people discuss about these basis operators. And here, I don't show you the basis because it's horrible. I just give you the number of operators, okay? The number of operators. Maybe this I put it here because we will probably use it later on. We can divide them in three categories. Bosonic operator means operator that you build in terms of gauge field or the Higgs only, and of course all possible derivatives. Okay? Then we have fermion bilinears. And then we have 4 fermions. That is clear that the fermions appear either 2 or 4. Okay, and these are dimension 6 operator. Okay. And so how many we have? Let me give you. I don't want to. Doesn't make sense too much sense to discuss the various classes. Also, there are subclasses here, but let me tell you the number of real parameters, which are the parameters that control the capital different operators, and the number of also imaginary coefficient, I mean phases that you can put in front of this operator. If the operator is Hermitian, there are no phases. If the operator is not Hermitian, there are phases. So here, okay, it's easy. There are only 9 and 6. Here there are more than 100, and here there are more than 1,000. Why? Because 4 fermions are operators of the type psi bar, for instance, q bar left I gamma mu q left j. For instance, say q bar I gamma mu right j k. These are the flavor indices. It's clear that we have many flavor indices. And if I just stick to the gauge quantum number, this flavor, okay, just this accidental series, so there are a lot of options, and I can combine the different pairs of fermions. So this is why you have this big number. This big number is related to flavor. Okay? Indeed, it's interesting to see what happens if I assume that. Remember, we discussed this U3 to the 5 symmetry. How things change if I impose an exact U3 to the 5 symmetry, which was the symmetry of the gauge sector of the standard model. Remember? So of course here nothing changed because these are bosonic, so they don't care about the symmetry. Here there are only 7 phases, and here there are only 25 and no phases. So actually this is the final sum here is 41 and 6. Compared to here that the sum is 1. So why I put this list? I mean, not to on the one hand to scare that people are really scared. You see, it's true. It's a true statement that the number of free parameters in this effective theory is written like this. If you only stick to these rules, which are the rules of the effective theory, a huge number. So there are more than 2,000 free parameters. However, the comparison from this to this is telling you that actually 2000 of these parameters are related to how you break the flavor symmetry. Okay, the different electroweak structure are very small number, very reasonable. Okay, it's a number that we can handle. While most of the parameters have to do with how we break flavor. And here comes the important observation that we should not be agnostic on how we break flavor, because already in the standard model Lagrange, flavor is broken in a very peculiar way. Most masses are very small except the top. Okay. So that was the first important message, but okay, this is it's important to know. So clearly, the message is that most of the parameters of these maps are related to the breaking of flavor. Okay. The point is, can we assume that U3 exact is the meaningful starting point? The answer is no, because U3 is broken in the standard model. Okay. The point is how it's broken. This is the key. So, as I always discuss when I give a seminar about this map, so navigating this space of coupling is making one need to decide how you want to break this U3 to the 5 sim. Okay, because otherwise we get lost in parameters. Okay, so then the rest of this lecture today, a good part will be related to hypothesis of how we break the symmetry beyond standard model. And I think why we have to care is because again, there is clearly we cannot assume to be exact because the standard model is broken. On the other hand, if we break it generically, we find problem. And why we find problem is maybe this, let me spend a few minutes. This we already discussed it yesterday, but I think it's useful to recap. Whatever that in the standard model, the breaking of flavor is very peculiar. The breaking of flavor comes from the Lagrange. Let me write it. So this is how we break U3 in the standard model is via this term. YU, YV. So for instance, as we discussed yesterday, if I compute a process like meso mixing, for instance, I couple my Q left I left J. So I want to build in the standard model, right? In the standard model itself, we consider the limit where the mass of the top is heavy. I generate contact interaction in the standard model itself. What is the Fermi type theory of this type? So this effective interaction exists in the standard model, okay, and is computable by this time. What I get in the standard model for this interaction, maybe we've seen it yesterday. Okay, you can do this calculation, and it, as I stressed, I think especially for the student, it's really nice to do this calculation. You can do it just using this Lagrange, okay, because it has to do only with the Yukawa sector, and here you have to insert the Yukawa coupling. And for instance, it's interesting to do it. You have to choose, you have to choose a basis, what you want to diagonalize. Let's choose, for instance, the basis where the down quarks are in mass state, okay? Which is convenient because it means that then I want to look at process where the down quark are my external field. For instance, this way I can compute B-bar mixing, K-bar mixing, B-sub-S mixing, all those are external down quark. So in the basis where, which means I rotate my Q and D to make this diagonal, and I call it lambda D. In that basis where I rotated this two field to make this diagonal, what is the structure of this? Well, the structure of this is this KM factor times lambda U, where lambda U is also diagonal. Okay, this, I guess you understand clearly the misalignment is only on the left because of the left here and this KM. So you see what I have to insert here is to left, here right is this term here. So here will be the Yukawa coupling element I3, okay, and so on. So from that simple reason, you understand that this is the standard model contribution. There is a loop factor, order one which I omit, and then you will have YU dagger square element I and the only scale is the top. And then when you, what is lambda U? Lambda U is the Yukawa coupling of the top. Sorry, of the up, which to a very good approximation is diagonal 0, 0, 1. Because I neglect the up and the charm masses and I have only my top is on 1. In that limit, what I get here, YU, is this sum here. I'm doing too fast. So you see, basically, I select only the third component of my VCKM. This is why I get here VCKM I3, which let me call it I top star, because it's the target, and then I have EK square Y top to the 4. So a very good approximation, this is the correct result, okay? And it takes a very simple one-loop calculation. So probably you have heard many times that there is the G mechanism. We also discussed in the first lecture, this cancellation. There is no cancellation. The G mechanism, the cancellation was, if you do the calculation, put in the W, if you want, in a wrong basis, okay? The truth is that everything comes from this term here, okay? Here there is no cancellation, simply the mass of the up and the charm are very small and the top dominate. The top dominance comes because of the large Yukawa coupling of the top. Is when you do the calculation, and here the only thing that matters is these things, which is, what is this? This is the Goldstone boson, which is inside the Higgs field, okay, which has the longitudinal component of the W. The point that if you don't do the calculation only selecting the longitudinal component of the W, then you have the full W, and then you have this cancellation, which is trivial. Well, now it's easy to say now it's trivial, but at that time it was not trivial at all. But now I understand really the only thing that matters for flavor is the Higgs, and then the longitudinal component of the W. And then if you do that, then there is no cancellation. The cancellation is simply okay. There are terms which are very small, and the dominant term which is the top. Okay. So then you understand why this goes with the, I think yesterday I put Y top square, so it's Y top to the 4th, okay? And you see that this goes with the mass of the top square, because this also is proportional to the mass of the top. And if you can rewrite it, okay, just for fun, of course, this, what is M top, this M top, I can rewrite it as Y top square B square, okay? And this times 2, I think, yes. And then the mass of the W square is V squared divided G squared divided by 4. So instead of V square, I can put V square, I can write it as 4 mass of the W square divided by G square. So if I put it here, this becomes, I hope I'm not confusing you, but I'm sure that the VA square, 16 pi square. And so here, the y top will cancel, so I have only y top square, and then this v squared by 2 to the 8. Okay, but then I have to put this 4 and w square g square. You see why it appears the mass of the w, but there is no w. Okay, it's just because I express v in terms of the mass of w, and then you can write in terms of G Fermi, and then you get the usual expression. And then if you write this in terms of the mass of the top, you will see mass of the top, G Fermi, and so on. But actually, this is much more transparent. Really has the relevant interaction. Okay. Yes.
No, just a consideration. So this is the if you want is what is happening for this operator. But if you want, the original argument was done in the opposite way, the G mechanism in the cancellation. So
it's super important also because at that time they showed that actually the things become
the charm prediction.
Exactly, because at that time there was no charm. So that was really the real breakthrough of Jim is the prediction of charm. So to show that the net that you have you need the doublets. A posteriori now it doesn't make sense too much to speak of a cancellation. Okay, so the cancellation is the cancellation.
No, but I want to say maybe CP violation and CP conservation things are different in the delta F equal to in the standard model. So what you're saying is perfectly right in the CP violation sector. Okay, you can do
also for CP conserving. I mean, this is general. Okay, the point that operators which violate that break flavor are due to insertion of the U cap. So if the point is, if the U cap goes to 0, the symmetry, the system is flavor blind. Everything you can do, whatever, there is no flavor violation. So all the flavor violations are related to the U cap insertion. Okay. And the interesting things, for instance, this box diagram, the penguin are typically they go with power of U cap. There are other things that goes with logarithm and that are a bit subleading, but it doesn't matter too much CP violation or CP violation. The key point of Jim is that now this we can do it because indeed everything we have doubled. So we have the theory. At that time they didn't have the charm. So really the idea of extending to complete the multiplet was fundamental. And you don't. The cancellation, if you want, is the fact that if you don't put the chart, the gauge part breaks down, and it's divergent because you cannot complete the theory. Okay, maybe we discuss later on, otherwise.
Mezz'ora, 15 minuti.
Yeah. Okay, sorry, then I'm going too slow. Yeah. Okay, so this is the standard model. The point that then, okay, our experimental friend measured these things, okay, and then if so the physical thing that you measure, or not, will be okay. Eventually, the standard model, which we just brought here, plus now if I put sorry, I raised my slab, which is now here I can pick in this list here, I can pick, for instance, an operator like 2 bar left I, gamma mu, 2 left K, 2 bar left. With coupling, as we call it, Ci divided by lambda squared. So if I put it, then here we'll have this coupling Ij divided by lambda squared. These things will appear exactly with this strength here, and then confront this strength here with this strength here. And the fact that this is very small for the argument we say here, because these elements are very small. Okay? And therefore, we deduce that these things also has to be very small. And now, if the coupling is of order 1, then I deduce this lambda has to be 10 to the 5 or 10 to the 4, depending on which process I look, but always extremely high. Which again is another statement of the fact that if you break the U3 to the 5 symmetry generically, you have problems. Okay. And so we have to make hypotheses on how to break. And I did this a bit in a rush to show you which is the minimal way, which this is what we did with Giancarlo some years ago. Really, the minimal way, or you want the maximal protection you can do, is to assume that these Yukawa couplings are the only source of breaking also beyond the standard model. Okay? Which is a very easy and consistent hypothesis to make. That is, the Yukawa coupling come from some UV scale. So let me give you with the picture. For MFV hypothesis, the idea is that there is some energy, there is some lambda flavor scale where you break, and then you generate the Yukawa coupling. Okay? For instance, this was especially the time when SUSY was fashionable. That was something you can do at the gas scale. You generate the Yukawa coupling. And here we have our retro scale. If we want to have something close by, let me call it lambda H to stabilize the heat. But here, so you need some new physics, but here your new physics is flavor blind up to this Yukawa coupling that you generate at a much higher scale. And this you can do it technically because the Yukawa coupling are numbers, so they are a dimensional object, okay, which do not scale with energy. They run very little logarithmically. So you can generate this breaking at some high scale, let it run it down, and so here we have a flavor blind dynamics, which is not the standard model, something else, but where the breaking of U3 is connected, it's only induced by the Y. How one do this technically, I think this is an important point. How we do this technically? Well, the philosophy is
a posteriori now. This could also be motivated, if you want, exactly for the argument you said, because it doesn't work like this for the neutrino sector. So instead, if you claim that there must be something at the same scale where it's generating the neutrino mass, then you can envisage two different mechanisms of breaking for neutrino and flavor. So if you want, it's justified even from this different point of view.
Yes, yeah, I think it from the point of view, theory point of view, this is the simplest and more technically sound solution. In 15 minutes, I'm convinced that this is not the right solution, but I think still it's an important one, and I mean, it's important, but now even experiment, sometimes it's becoming less favorable. It's still possible, but it's slightly less favorable. But so let me first discuss how it works, because technically it's important. So how it works? Okay, this is a bit more for the student. I mean, this is what we usually call the spurious technique. That is, we basically attribute to this object a kind of quantum numbers. Basically, we treat them as field that acquire a value at some high scale, and then given this value, then we have the thing. So how you do that? These things from the point of view of flavor symmetry transform as a U3 Q. Actually, this is a 3 bar of my flavor symmetry Q. this U right is a tree of my flavor symmetry U, so then I need to declare that this YU transform as a 3Q times 3 bars U. So I attribute to this YU non-trivial quantum number under my flavor symmetry, particularly in this case, what I'm interested in is SU3Q times SU3Q, okay, which is the global flavor symmetry acting on these two guys. If I say this one was transforming like this, actually this object would be invariant, okay, but then this guy gets a VEF and does the job. So then the idea is that if you compute your scattering amplitude, okay, and then you insert expectation value of this Yukawa, and it's only via that insertion that you generate something which is non-invariant under flavor. Therefore, flavor is completely controlled by the VEF of this Yukawa coupling. Okay. Again, this is a very nice, consistent approach, and it's clear this way you really mimic what happens in the standard model. So then when I compute my operator, this operator Q bar left I mu to F J, right, like this. This is not allowed. Why operator which is allowed is this one where I put Q bar left, then I put the Yukawa coupling darker, and so this way, this object here, I, J, J, then this is formally invariant, exactly as this one was formally invariant, okay? So this is exactly the result of something like this. So then I can have it, for instance, I can have this, where this is allowed, put on the square, but then here, when I compute, I get exactly what we know, y t square b t I b t j, which is exactly the same suppression that we have in the standard model. So this way we explain why the coefficient of this operator is very small, because it has to pass through the Yukawa coupling, which is very small. Okay, this is how it works, and then the bounds become much weaker, because then this has exactly the same parametric structure of the standard model, and therefore the suppression is only between the W scale or the top and then this lambda. Okay, and then if you look at the precision, is 10%, so you go up to 1 TeV, not much more, which is nice because we want to have this somehow at the level of 1 TeV. Okay. Okay, so this is the MVP principle. I'm going very fast. Okay, actually, it's already a bit old, but still, I think it's a nice principle, and this is really a nice tool in effective theory. This playing with the sputter. That is, we have these symmetry, global symmetries. You make hypotheses on how you break it, okay, and then consistently, then you can keep track systematically with this Fourier technique of how you break the symmetry, and you make an hypothesis of how you break it. In this case, the hypothesis is the minimal one, that the breaking is only given that you break our cap. Again, this was fitting very well in the pre-LSE era, right? Because all the other bounds on all the other operators were relatively weak. The only very strong bounds were on flavor, and this way you could lower the bound of flavor. So now, why I said now it's becoming less appealing to some extent. First of all, look, one intrinsic weakness of this is also doesn't explain why the Yukawa are what they are. Okay, you have to assume that there is something which is okay. This is already first a bit disturbing. But second point, now really being on the other hand pragmatic, is the stabilization is the allowance of a low scale, which is problematic here, at least with only this. Why? Because this symmetry here you don't have any protection for an operator like this. Here I'm summing over the flavor. So this is a flavor single. So you overlap you summed over all the generation. Yeah. Okay. This is flavor invariant, flavor blind. This is also flavor invariant on the left sector. This operator, according to this rule, has no suppression. This operator, however, contains, for instance, u bar u. This one contains mu bar u, okay, or e bar e. Now, the recent bound from LSE of operator of this type, which will be an operator to do Drell-Yan mu mu with no suppression, with up work, it's 15 TeV. Terrible. So you basically LSE is telling you this case should go up, and then you have a problem with it. So you cannot claim anymore that there is a, if you want to keep a low scale, okay, you cannot defend it with this symmetry here, because operators of this type are not protected. And it's not only this one, okay, there are all the operators which are kind of flavor invariant, which contain light fork and light leptons. Here the bounds, the direct searches now are becoming quite strong. So the bounds are typically at the level of 10, 12 TeV, which makes the possibility of having the mechanism here to stabilize the Higgs less likely. Okay. This is why I think, again, there is nothing wrong technically in MFP. Worse, it lowers the bound. It's the most efficient to lower the bound for flavor physics only. Okay. But now we have other bounds, which again, 20 years ago we didn't have, which come from collider, which are on flavor universal operator, which now become very strong. So this why I think it's interesting to think of different options, and the different option.
So you're buying a Rattazzi statement then?
Never.
But he says minimum flavor relation is the most pessimistic scenario.
Okay, this was always true that it's pessimistic. I was pessimistic, but I think now I think once 20 years ago was the most effective in lowering the bounds. Now it's not anymore the most effective. Well, still in flavor is the most effective, but
too effective.
No, I think it's not effective on the flavor conserving part. This is the point. So it's not effective on the flavor conserving operator, which is okay. It's a fact because that was only designed to protect flavor. So the point is really are still these other operators which are flavor U3 exact. Okay, here there are for some of these operators on the fermion bilinear, on the 4 fermion operator, which are in this category, even U3 exact. Here there are strong bounds. Okay? So if we want to keep the option of stabilization of the Higgs, so some dynamics that coupled to the Higgs, and remember what I told you yesterday, if it coupled to the Higgs, you should also couple to the third generation, because the Higgs is coupled to the third generation. So this is, you already see the solution, okay, the solution, the hypothesis is that you have to decouple the dynamics of 5 generation from the dynamics of third generation. Only doing that, you can allow to have relatively low scale dynamics for the third generation and the Higgs, and have a different dynamics that involve only the light generation. So, but one has to be careful because this means breaking flavor, treating differently the light generation from the heavy generation. So we are going to an intrinsically completely different paradigm if you want. Really now I want to take flavor really more seriously in a sense, and try to build, at least in my DFT, a separation between high degrees of freedom and heavy degrees of freedom, which means I don't want to look at anymore to U3 symmetry, but to, for instance, the U2 symmetry, what maybe after the break. Okay. So this is a good point to stop. Yeah.
And before we go to coffee break, may I ask what are the measurements from LHC that standard model fits of the or yeah, something. Yeah, so basically Drell-Yan includes.
Drell-Yan are the strongest one. However, so Drell-Yan kills all the same electronic operator, but then there is also CPR 2Z. This will are slightly less severe as this, but still very strong because here there is QCD background, but still these also are very strong, and this put bound on the 4-quark operator. Okay? Really on the 4-quark and the same electronic, these are the strong bounds. Very easy, but it's telling you that too simple, okay, the message is too simple dynamics like this one cannot be at the quantity scale.
Even the experimental signature is quite striking. It's not complex fits.
Exactly. But this means that we have to be a bit more inventive. It kind of, you want to attack the Higgs, the third generation, but without touching the light generation. That is the
Okay.
Okay, so I think this, yeah.
Urgent questions before going to coffee break?
Yeah, please.
Looking at this description, with the mass of the top, which is the most important kind of diagram, is there some similar description in the lepton sector in which the mass of the top is played by the tau mass? And the new physics, so we have to set new physics both in top sector and also in the tau sector.
Yeah, what I'll discuss next, yes, in a sense, because then I will separate the third generation. So for this type of, so in the standard model, the tau Yukawa coupling is small. So there are no big effects induced by the tau Yukawa coupling, right? So in the standard model, there's nothing too special with the tau, and also just don't have breaking of large breaking of frequency in the tau. Also, there is no mixing in the flavor sector. So in the standard model sector only, there is really the top is the only one which is big. However, what I discuss next after the break is that on the other hand, if we really want to separate third generation from light generation, then you have to do it in a way which is consistent with the gauge symmetries. Then you have to put the full generation because otherwise you get problem with anomalies and so on. So there, in this other class of model where I separate third generation and light generation, there you can, tau physics is much more interesting because indeed not related so much to the tau Yukawa coupling, but to the fact that tau, like all the third generation, could feel a different force or interaction.
So this kind of sector is included in flavor violation.
No, so it's not including unification, but it's including this U2 approach which I will discuss. Because I try to give a bit of historical stuff. I think unification is the starting point, and I think it's good. We will save some of the unification part, but only for the light generation. Okay.
Okay. If there are no other very urgent questions, we can go to coffee break and reconvene at 12, at the quarter to 12. doing it.
Okay, so what I basically already advertised is that we have to somehow change hypothesis and try to split the treatment of the light generation versus the third generation. And first of all, let me tell you, so this is, I think it's an interesting idea. There is quite a lot of development in the last few years about that. And this is dictated also by what we observe in the Yukawa coupling, okay? Not only the Yukawa coupling break the ferrosymmetry, but they break it in a very peculiar way. So if we look at numerically to the Yukawa coupling, and you ask which are the Yukawa coupling, if I take, so this contains all the masses of quark and leptons of auto generation and CKM. If we switch off, okay, all the entries below 10 to minus 2 in the Yukawa coupling, what survive? Okay? The only thing that survive are y top, which is about 1, y bottom, which is 2 10 to the minus 2, y tau, which is, and I evaluate this Yukawa coupling at the electron wing scale, okay, because they run. All the others Yukawa coupling are small, well below 10 to minus 2. The charm already running up at the scale, it's well below 10 to minus 2. So these are all the third generation. And basically you have to keep BCP, because you see here, when you look at this multiplication, so these are the eigenvalues, okay? What is the form of the up? So basically, let me first do the bottom Yukawa coupling. Roughly is like this. So there is y bottom, and all other entries are 0, while the up Yukawa coupling is y top. And then when I multiply by the CKM, here I have y top BCBTS, and y top BTTs. And here there is something. And this suggests maybe something for you. Suggests something that indeed really numerically, okay, in the standard model Lagrangian, there is a kind of emergent, or one more accidental, but this is really different type of accidental. There is an effective U2 symmetry. That is, the light generation are essentially massless, and the gender big mass. So it makes sense to consider a scenario where, rather than considering U3 to the fifth, you consider U2 to the fifth, which is now we can discuss, of course, we can make different hypotheses. We can even consider some U2 and some U3, because indeed also these Yukawa coupling are small. We can even neglect those. However, we have to be careful, because we want to find a symmetry, a global symmetry, global flavor symmetry, which is also compatible with our standard model gauge symmetries, right? And if we treat separately these 5 different fields, we have problem with gauge anomalies. So I think this is why it makes sense to start from these so clear rather than having something more mixed. And so what is the idea is? The idea is that at some high scale, you break from U3 to U2. And then what really matters in the low level, this lower part here, is a dynamics which, in first approximation, respect these U2. And again, here, it's better than MLP because you already have an indication from your Lagrangian, the dimension fourth part Lagrangian, which is almost U2 invariant. Okay, so this Lagrangian was not U3 invariant because of the topic of a coupling. So clearly, again, if I just neglect small entries here, I observe that my Lagrangian is approximately U2 to the fifth invariant. It's nature that is telling me this. Okay? And so we try to exploit this better. And also you see here, maybe sorry, written this. Let me try to get that stuff. So the down you have a capital is YB. The top you have a capital is and here. You see, these the only terms which actually in this limit that somehow break the two symmetry are those BTS and BTD, which is the mixing between the third generation and the light generation. And this is a kind of vector that goes from the third generation to the light generation. And actually, if you remember, this was the things that we had when we were computing meson mixing and so on. It's always controlled by this term here. So protecting the full Yukawa coupling, that is what we were doing with mean evaluation, was a bit of overshooting. What we need to protect is this, that is the mixing between the third generation and the light. All the rest are small. Okay? If we keep them small, it's not a problem. So that is the idea. So we have to know to save a mean evaluation the protection of this, which is the protection of how we break U2, and all the rest, on the other hand, we can be more agnostic. And that is again motivated by the fact because if we do like this, so we basically now decide to partition our SMEFT in a sector which involve only the light generation, so those which are the field which are charged under this U2, and the third generation. Okay, so the statement is that my fermion field, which have the generation, I declare that my fermion psi will be, for instance, what previously I called U, okay, left, I. Now I will split into a term which I will call U3, okay, and something, let me call it the tilde. So this is something that is charged under U2, while this is tilde. So this is the doublet of this U2, while this is. Okay, that is there. And the only thing I have to be careful is that for all the attended field, no problem, this distinction is very clear. So the distinction between the right-handed bottom is separate from the right-handed strange and the right-handed up. Only in this sector of the left-handed, you have to be careful because indeed there is a mixing, which is these things that we have to treat properly. And the hypothesis is that this is the only relevant breaking of this U2, which somehow connect the third generation, particularly in the second year, between these two here. So this we treated as the only relevant source of U2 breaking. Okay. So with that, the idea is to build a different construction. Sorry for that. I told you here, the problem was that this separation started to be quite high because I was not able to keep all the operator invariant under U3 at this case, so I have to push it up. While here I'm doing a different hypothesis that there is a lower scale, which I call lambda x, but also lambda 3. So it's the dynamics that affect the x and the third generation, which is, I want to keep it as low as possible, stabilize the x. And here I have something which is invariant. Okay. And finally, at some higher scale, I will generate the masses for the light generation. No, like here. But the idea is that we have a separation between the dynamics which happens here respect only the U2 symmetry, not the U3 symmetry. And this allows me to somehow, again, it's a hypothesis, but this allows me to separate the dangerous operators, which are those which are very much constrained by LSE, for instance, those which contains muons and light quarks, from those which, on the other hand, I need to put here to stabilize the Higgs. And again, since the Higgs is strongly coupled to the third generation, because the topic of this makes sense. And also is an a posteriori justification of what we observe in the new Kawakami. So you see, from this point of view, it's a better, again, bottom-up hypothesis on how to partition the spectrum. Do I convince you? And actually here, if you do the counting operator, for instance, this was the counting for that. If you do the counting with U2, just for your knowledge here, the number of operators is 120, so it's a bit more, right? Simply because basically you have to double here the proximity operator to distinguish those that involve only third generation and those that involve light generation. There's a bit of that. So it's not a too big task operator. And let me tell you, for instance, we did a numerical analysis, so we look at the bounds on all these operators, which are under pressure, it's not too difficult. And then we find that the operator that involve only the third generation, or third generation and the Higgs, can be at the scale which is between 1 and 2 t. So, at least from the point of view of a pure EFT approach, makes sense. So, I mean, I've not solved the Higgs problem, okay, but I defined a EFT setup which allow to implement the possible.
So if you want, is a more you have released some freedom you had on the U3 to a more to a moderate symmetry, just the one necessity if you want to solve the flavor problem.
Not only, but yeah. So I think why I think this is better, okay, in a pure EFT approach, because on the one hand, I explain the structure of the Kawakami. So the structure of the Kawakami in first approximation is something that there is something sizable for the third generation, not even too big, and then something very small for the light generation. So a posteriori, I explain the Kawakami. So the same dynamics which is responsible for these things has to do with the generation of the Kawakami. Okay? And then also I free a space for solution to the Higgs hierarchy problem involving Higgs and third generation. Now, okay, the next step I would like to discuss is, okay, this is just a pure EFT, but probably also you start to be bored about EFT. We have also to make hypotheses. I mean, what is a U2 symmetry appears? You see, the nice things here of these things that the U3 to the flavor symmetry, how we deduce it, was the symmetry, was the accidental symmetry of the gauge sector of the standard model. So that was a nice motivation. So this U3, we didn't take it from the sky. It was given by our gauge sectors. The gauge symmetry was invariant under this U3. How can I justify U2? On the other hand, I really, well, I put it somehow by hand by the observation of the Kawakami. Would be nice to have this symmetry rather than declaring it as a global symmetry. We never like to declare global symmetry. We want to have global symmetry emerging as accidental symmetries. And then this naturally point to the idea of non-universal, flavor non-universal gauge symmetries. And this is what I discuss next. So now I go a bit faster. And this brings to the concept of what we call flavor deconstruction. So, what is this idea? I think it's very simple. Again, also something as usual old, but that we some kind of revisiting here. The idea is that we have different gauge symmetry. Let me call it gauge symmetry G12 that are on the fermions of the first two generation, and exactly the same group, but acting on the third generation. Okay, like for instance, get the color. here I have an SU3 active on the light generation and an SU3, again an SU3, but on which only the third generation and the Higgs are charged. And then, of course, I at some point have to invoke a simply breaking, and then I break to the diagonal group, which has to be should contain standard model. Okay. Why this is nice? Because at this level, when I have this symmetry here, this group here, clearly here there is the emergent symmetry, because this would be the fermions which are here. Okay, I can mix them, so the gauge symmetry would be invariant in this space of fermions which are only the light generation, while these other fermions really feel a different force. So the U2 in this case emerge as an accidental global symmetry of this different gauge sector. Okay. And there are a lot of nice things about this, because first of all, if you start with a structure of this type where you have two groups, okay, and you want to break to this is the diagonal subgroup, okay, as you know very well, SU2 cross U1 break into U1 electromagnetism, or you know SU2 left, SU2 right break into SU2 vectorial. It's not a chance that if you have a breaking, you always tend to break to the maximal subgroup, and the diagonal subgroup is always a maximal subgroup. So these breaking mechanisms do not require any tuning. It's completely natural. Okay? You don't, provided you have some fields which are charged under both, you will always find the minimum that takes to the diagonal subgroup. It's a general group theory taking, right? And so this type of breaking mechanism is not complicated. And so and then how it works. So, a posteriori is explaining very nicely the structure of the Yukawa coupling. Let me do an example here, and then we discuss what else. But this is really the big picture. Okay, let me give you an example. So this I should tell you what this G is. Let me do an example. We call it deconstruction because indeed this G13 is a group which is flavor universal, and we deconstructing something which is not flavor. So the idea is that in the UV you don't unify in flavor, you de-unify in flavor, you deconstruct in flavor. Or maybe you unify in terms of, on the other hand, quantum number. So maybe you can go to a Pati-Salam, but then it will be three different Pati-Salam or two different Pati-Salam. Let me do an example which is very simple, which is hypercharge. So let me start deconstructing hypercharge. What happens? I have to decide which part of the gauge symmetry I deconstruct. I don't need to deconstruct everything. Let me do the simple case, which is hypercharge. So the idea is that we have an hypercharge 3 and an hypercharge 1, 2, and then at some point we introduce a field that will get a VEF, and we break to a standard model hypercharge. So this field has to be a bidoublet of this. I get a VEF exactly like the Higgs break SU2 cross U1. So what happens before doing the breaking? For instance, if I want to write the Yukawa interaction, if I have psi 3, and in this symmetry I charge the third generation and the Higgs, and here I charge the first and the second generation. So this operator is allowed, okay, because here the flow of hypercharge, okay, goes from the hypercharge of the Higgs compensate the different hypercharge between the left and the right, exactly as in the standard model. Right? Here I put psi, but you can do it for any of the standard model fields. While maybe this I call it 3 to remember that the Higgs is charged under this group, not under this group. So here this term, for instance, when I want to do this is not allowed, okay? I cannot write it because this term is charged under a different gauge group, so will not concern the gauge symmetry. So this explains what is in my blackboard why the Yukawa coupling 3-2 is small, because it's not allowed. Of course, the idea is that this I will build it with some higher dimensional operator. I put, for instance, a heavy fermion. Okay. And then here I have the sigma field. So here you see the flow of hypercharge. So here I have hypercharge. This is the hypercharge 3 that via sigma becomes hypercharge. So sigma, in this case, is very simple because it's just a U1. The sigma, the quantum number of sigma is, let's say, in this case, I have to tell you, it will be x minus x. So we'll compensate the aperture of this heavy fermion here, which has the same aperture of the third one, and make it the aperture of the second generation. And therefore, this term here that in the standard model will give me VCB will be a suppressed effect because of this heavy propagator. And of course, we have to choose properly the expectation value of this guy here. But the idea is that you have is y3 2, which goes like the VEV of sigma divided by the mass of F, and this F is a vector like fermions, which can be heavy, and therefore I explain somehow if this ratio is small. Well, I explain why VCB. Of course, I don't explain. I really have a rephrasing of why VCB is small because it's not an allowed term by my gauge symmetry. That is that. Okay. So I think this is a nice, and here I just deconstructed hypercharge. One can deconstruct any of the different gauge, different pieces. Yes.
Is it necessary to deconstruct all of the three components of G321? So you deconstruct the hypercharge. Do you need to deconstruct all the three components?
You mean a component in flavor or of the gauge group of the standard model?
Gauge group.
That's a very good question. So you need to construct, if you want to explain the Yukawa coupling, you need to construct at least two. Because you see, the Yukawa coupling is one can, if we demonstrated this, and actually it takes a bit of time to demonstrate it, but it's not too complicated. And maybe I can show you indeed. Let me see if I can show you this better. So I want to explain the Yukawa coupling. Okay. So I want a symmetry that somehow forbids all the Yukawa coupling except that one. And the Yukawa coupling are those written there here. For instance, if I deconstruct SU3 color, okay, I would forbid all terms except the rejection, but only for the quark and not for the leptons. Okay. If I do it with hypercharge, it also really doesn't work. I mean, explain the suppression of VCB, but it's more complicated here. The simplest thing is to deconstruct two of them, and you can choose which of the two gauge group, or you can also deconstruct them all. Okay, and yeah, okay, I don't know if this is enough to explain. So the point is, you have to depending on the point is that maybe the simplest way to understand is the Higgs it's couple always this left right field. Okay, basically the nicest way is to deconstruct a field which acts differently on the left and the right field. Okay, and this way you automatically explain everything, and also you have a way to control separately the smallest of the diagonal entries and the smallest of the diagonal. For instance, a nice way would be to prototype is now let's promote our symmetry to this one here. Right? If you remember, was the constrained symmetry that we defined. It's clear that if I deconstruct these two guys, it's perfect, right? Because if I deconstruct SU2 left and SU2 right, and then I have it one for the generation, one for the right generation, then I would really have the suppression factor here on the two fields. So only when I have third generation left, third generation right, and the Higgs. So the idea is that these come from an SU2 left 3 times SU2 right 3 times an SU2 left 1 2. And then you need two different breaking. These two going to left, and these two going to SU2 right. And you have to introduce two fields. One will control the smallness of the left-handed mixing, which is the CKM, and the other one will control the smallness of the right-handed part, which is basically the entries in the eigenvalues of okay. It's not the only option, but okay. I hope this gives you a glimpse of what type of game you need to do. Okay, what is nice is that you basically end up with a sector, which is the one here, which contains the Higgs. This third generation has some extra fields that you have to include to generate the Yukawa coupling, but all these fields can live at the TB scale. So they don't feel strong bounds because they are all charged under these. To pass to the second, to the light generation, you have to pass these mixing terms which are suppressed. So at the same time, explaining the suppression of the entries here in the Yukawa coupling, you also explain why some of new physics couple less to the light generation. This is not coupled to the light generation at a heavier scale. So the idea here is that there is some scale, let me call it lambda 1, 2, where you generate. So this is the scale where you are above lambda 2, here you break full non-universality. So here you distinguish between first and second generation. Below this scale here, you basically freeze the breaking of first generation at the scale here, then you arrive to this scale lambda 3 and lambda h, where here you have these U2 invariant. So here your gate group is B12 times B3, and finally below this scale you break here to be 1, 2, 3, which is the standard body group. And here above you even have maybe G1 and G2. Then take to G12 and then break to G12. So it's a cascade of breaking, which you say maybe I told you at some point we have to make a hypothesis. And there's a lot of hypotheses, but it's a nice set of breaking which would reflect in the Yukawa coupling. So this hierarchy in the Yukawa coupling somehow reflects this hierarchy in scale. Okay? And for instance, one can justify this in model with extra dimension, but you also justify in normal 4-dimensional field theory. And again, the advantage here is that we can keep this scale low, okay, which complies with the current LC bound. I don't want to oversell this, or will not go into specific technical detail, but I hope you understand the picture. And again, I try to do this in a bottom-up approach, and I try to infer it from the EFT approach. Then, of course, if you really want to make hypothesis, then you have to specify which group you want to deconstruct or not. And if you deconstruct it, you expect gauge boson coupled to the third generation different than gauge boson coupled to the light generation. Okay. And the lowest one are those coupled to the third generation. And again, the nice point is that there is there is the choice of scale, but these scales are stable, and there is no tuning in the for example in the gauge coupling, okay? Because whatever you start with this gauge group, if you have identical gauge group, automatically the diagonal subgroup has a unique coupling for all the generation. You don't have to adjust the quantum number. So the fact that, and again, this probably the best example, again, think about electromagnetism, no? And if you start in electromagnetism, we have electron left and electron right that have the same charge. Do we adjust it? No, just because electromagnetism is the subgroup of SU2, so we start from and U1, and we already seen is now embedded in SU2, right? And here the subgroup, okay, is this is the breaking that the Higgs does, okay, from SU2 cross U1, and U1 can be embedded in SU2 right to this SU2 F plus I. Okay. Here the gauge group, so it's like this. So here when we look at the electron left, and the electron left is part of one multiplet, and the electron right is a completely different chart. So very different field from the point of view of this symmetry. Okay, so the gauge symmetry here, see these two as completely different objects. Really different. Okay. So we don't think about this, but then when you go here, you have only an electron field and the gauge field that sees the electron left and right identical. And we have done any tuning to let the electron simply, the only thing that happens is this breaking, which selects the diagonal subgroup. So we go, in this case, we go from non-universality in helicity, okay, to universality, so to parity, emerge as a low energy symmetry. But we start from a symmetry which is here the gauge interaction is non-universal in helicity and becomes totally universal at low energy without any adjustment. The idea that the same thing could happen in flavor space. We start with something which is non-universal in flavor space, and at low energy, flavor universality emerges as an accidental symmetry. Like here, parity is an accidental symmetry of the theory, okay, because of is the infrared symmetry, but it's not the symmetry in the UV. We always discuss how we have three identical generations of quark and lepton. This statement is misleading. I mean, they look like identical from the point of view of the long-range forces that we have seen. But in the UV, they can be completely different. There is no guarantee that they remain to be. The old idea, this field which was coming from supersymmetry, was that the gauge symmetry remains untouched up to the cascade. That was the prejudice. We always thought, okay, there is SU3 cross U2 cross U1. We put supersymmetry, we don't change the gauge group. Here, the idea is that we change the gauge group, which is a discipline that we have. Okay. I don't know if it's true, but I think it's an interesting possibility. Okay. Did I convince you about all this? Good. So if you let me change completely subject. Since I have 15 minutes, since this lecture were about the standard model EFT, okay, I thought I want to give you the final discussion of something different, which is, despite this math, every good fractional community accept this is the nice EFT standard model. Not everybody agree in the sense that all this counting operator and so everything. I assume that the Higgs is a doublet, okay, of SU2 left, which some people object. Maybe not the case. So let me discuss this final part here. It's beyond this math. Goes on the name of which is the whole Higgs effective theory, which is we can try to take a different road and don't give for granted that the Higgs, the 125 objects in matrice is part of the doublet. Okay? And definitely the object is there, but the point is that we can separate the part which is charged under SU2 and the things which are observed, which can be treated as a singlet. And so here I have to go back to what we discussed yesterday about the constraint singlet. Remember, we introduced this field now, which was remember we see this with the in the so-called linear realization, where we treat the Higgs as a doublet, we can build this object here, sigma, which transform under SU2 left comes with SU2 right custodial, where we gauge only that component. Right? Well, a bit inspired by what happens, for instance, in QCD, where we have a kind of similar symmetry with the breaking via the spontaneous symmetry breaking of the fermion condensate. One can think that maybe something similar could happen in the standard model. And actually, this is not the old idea of Technicolor. Let me rewrite this guy here. When I can write this field in the usual notation like this. So here I separated explicitly the H field, which is our this component. Now you know that right 0 here on the diagonal. This when we go to the unitary gauge, this is just B plus H, which is what is written here. So this matrix here, I can decompose it as the modulus part, which is B plus H, and this unitary 2 times 2 matrix. So this is the matrix that contains all the Goston boson, and the unitary gauge, this goes to that is sorry, hope I'm not going too fast. And the idea here is that so in the linear realization, so if I treat the Higgs as a doublet, basically this sigma will have this combination of U and H always in this form. I cannot break it. On the other hand, this possibility is to somehow separate this H and this U and treat them because they have different transformation property. So this is really the object that carries the SU2 transformation property, but this is a singlet. Okay. However, this is the nonlinear realization of the spontaneous symmetry breaking. So this one is U is into the I sigma. Okay. So the idea is that I can treat separately these I, which are the Goston boson, those that will give rise to the longitudinal component of the W, and this H. So the idea of this hat is to the Lagrangian where I treat H and U as independent objects. Right. And I want to convince you that this is clearly a bit fine-tuned and actually highly tuned. So I'm not really a big fan of that, but it is something that people discuss it. So I think it's worth to see and also to get convinced of which type of tuning required. I mean, it's not a completely crazy idea. Of course, so this field is here, and the point is that if there is, for instance, some extra singlet field under SU2 scalar singlet, it can mix with this guy here. And therefore, it's natural to think that what you measure in experiment somehow is a mixture of the part coming from a doublet and something else. And therefore, again, in an EFT approach, you have to treat separately. The single component, the object seen in an experiment is neutral as no charge under SU2 left, right? A priori, can be treated as a singlet. That is the thing. So how it works?
Sorry, but the gap between a sigma, there is a mass gap between the nonlinear part and this extra particle. There is a mass gap between.
But so these are massless, okay? These are because both are massless. The point is if H come together with V, always in this combination of no. This is how the problem boils down to simply this statement. Do V and H appear always in this combination or not? Okay, it's as simple as that. And you see, this is the, and you can understand it very easily. For instance, let's look at the kinetic part of the X. Okay? Now, written in terms of this sigma will be this. Okay. Now, do a little bit of algebra here, and if you now I do it. This is in the standard model. Okay, it's like this, and if you do the calculation, you'll see that you have to act with the covariant derivative. The covariant derivative on H will give nothing, simply a normal derivative. So this term, if you do the algebra, give you the result. Okay, just not to put all the right factors so we don't have too much time. Okay, you will get I put the V in front. Okay, this is still our standard model Lagrangian. We've written in a more fancy way. And you see these terms here, this is this unitary matrix that when I go to the unitary gauge, this will contain only the covariant derivative that contains the W. So this is the term that give rise to the mass of the W. Okay. So this will give me but here when I expand and the size, because here I get something like this. So it's the well-known statement that you have the mass of the W, but then the Higgs is coupled to the 2W exactly with the strength which is also given by the mass of the W squared. Right? So here you expand this and then you get times square. And here is this is yeah. Just keep this notation with the H over V and plus the term with 2 Higgs. So you have the prediction that the coupling of the Higgs to 2W is just given by the W mass. Right?
There is a trace.
Yeah, sorry, there is a trace, absolutely. Yeah. Right. Yeah. Right. Sorry, well, fast, but I wanted to make you one on this. So in this left or right, people say, well, this the principle could be something like this. F of H over V. But this function is 1, okay, by normalization, but plus there is a coefficient A over V. So this is the most general non-linearization where you allow a singlet to appear generically. So clear that you have to, this finally will give you the mass of this, you have to tune this coefficient C to get this term here, which now is measured to 10%, so even slightly better. So still 10% is not too terrible, but this is the type of tuning. And so, but the final things I want to tell you, if you still allow me 3 minutes, is that, yeah, if you look like this, it's not even too bad. But the real bad things comes when you look at the breaking of the custodial symmetry. When we go to consider our higher dimension operator, for instance, in the SMET, okay, we can write so this SMET is the theory where I treat sigma as here. I treat this object as a unique field, which in this is my doublet of SU2 or my doublet of SU2 cross SU2, and I don't break it. While this heft I break and I keep this generic function. So if I don't break it, at dimension 6 I can write something like this. So here I put T3, and I call it T3 right. You see, this is an operator which I can write in the SMEF at dimension 6, because you see there are 1, 2, 3, 4 sigma and 2 derivatives, so the dimension 6 operator. This is compatible with the gauge symmetry, because I put here T3 right. And remember, this is okay from the point of view of the gauge symmetry, because the gauge symmetry are only on the attended. Remember, hope you followed the lecture yesterday. So this is allowed, and this is a custodial symmetry breaking term, because indeed it contains only one generator of SU3, but it's compatible with the gauge symmetry, which appear at dimension 6. And this will give me a correction to the mass of the Z with respect to the mass of the W, because this, if it contains T3, will affect only the mass of the Z. Yeah. The problem with the heft is that now these things you have it at much lower dimension, because now you can write now we put it other function, and then I can write the same structure here. But now this is an operator of dimension 4, if you want, of dimension 2, because U as dimension is a number. Okay, and I put this normalization here. So this will modify the Z mass with a much higher strength with respect to this operator, because this is, I can suppress it arbitrarily, putting this scale to 10. Well, I don't have any more the power here. Okay, and actually here, well, here, if here the tuning was 10%, the tuning here is 10 to minus 3. Okay, so I just wanted to conclude with this fact that, okay, playing with the evidence that treating the Higgs not as a doublet, I think it's very dangerous. Okay, so I don't know, maybe it was a nice way to conclude the lecture, but I think it's a completely different thing. Also, that not everybody agree even to treat the Higgs as a doublet. There are different, but clearly this requires more tuning and more subtle treatment of. Okay, so sorry, we went a bit ahead.
So let's we have now half an hour of discussion, right? Okay.
Okay, so then actually we can discuss.
Okay,
I think this is for everybody. If you want to understand, I'm sure, even if I don't know, if you want to understand more motivation and discussion of this, listen the seminar on Wednesday at CERN colloquium at 2 o'clock. Because Gino, what is the title of the talk?
Yeah,
I'm sure.
Sorry, no. Yes, I will give a colloquium at CERN next week.
Okay,
that everybody can follow online because it's public, and it's about the FCC. I mean, the motivation for FCC for this future for life.
Good to know.
Yeah.
Any comment?
Question?
But okay,
One is this thing also will affect the quadrilinear coupling of the WW, or
Yeah, of course.
because of course it will give you a terms which is WHH, which changes that.
But that we know even less.
But
Yes. So actually, the strongest constant, I think, if you just stick to this, and the strongest constant come from X to W.
Okay. But another point is when you show the model of the breaking of the gauge symmetry, then one has to preserve the TV scale, let's say, for the and what are the strongest limits in this context to that scale, or in another way, which is the most crucial experimental input which can falsify this the idea of the scale?
Yeah, this is a very nice question. Yeah, so I think searches, so the really unambiguous bounds are searches for third generation particle in the final state at LSE. So, for instance, PP, the very strong concept comes from PP to tau, but also PP plus X. Also, PP bar plus X. So if that idea was correct, that when you break your P12 times P2, as we call it, standard model, clearly here, here you have, suppose you do it with color, clearly here you have 8 gluons, here other 8 gluons, so we have double number of 8 gluons. 8 combination will become our beloved gluons, but then there will be 8 massive gluons, colorons, that will couple mainly to the third generation. Actually, we also couple a little bit to the first generation, but the couple to the third generation will be bigger. And these, for instance, will show up in PP bar, PP bar. If you deconstruct hypercharge, you will have a Z prime. It does exactly the same thing, will couple to third generation mainly. And so will contribute, for instance, to this. If you couple SU2 left, also. So unavoidably, you will touch some of these.
Changing the cross section.
Changing the cross section with respect to the standard model.
Yeah. But, and then you have the keys. I mean, you are focusing or producing with collisions some final states. There is also space looking in decays of stable.
Yeah, for instance, of course, in B physics, there's a very interesting thing. So, for instance, indeed, there are even some hints if you want to be optimistic, like this to charge tau and trino. This is a very nice process because this is third generation, this is third generation, this is third generation. So this is very much third generation except one second generation. And so here, especially here, if you break any of the group that contains, in particular, in one group which I really like, which is where this group will be SU3, 1, 2, but this is SU4 of Patisalam, but for the third generation. Okay, this is a very nice setup where you have these two groups. Maybe this comes from an SU4, but at much higher scale, but then it's broken to this. And then you end up with these two things. The breaking here give you normal color. Okay, because exactly when you have a higher group here, the SU4 times SU3, this is really like SU2 cross U1, you go to SU2. The diagonal takes the smaller of the group, which is SU3. So here you have SU4 with the leptocore, SU3, color only for the first generation, and then you break to color the normal color. From this breaking, the massive field that you have is the leptocore coupled only to the third generation. For instance, it's perfect to explain. You would see here, coupled to tau, and with the small mixing that you have, we also coupled to sharp here, PKM. So this, maybe some of you know, there is here an anomaly, since 10 years,
Yeah.
which is not okay. I don't put my hand on that, but it's nice. I put
Anybody has friends? Yes.
Yeah, but we did a lot.
But I think that is
Lavaro tu.
perfect. but it is not the only one. For example, if you go to DS, new is also very nice. Okay, and this would send you also to the Z prime. So here you also have a Z prime. Okay, and you also have this column. Okay, so you have all of them here. A lot of generators. So, but this is beautiful. All this, the color you will have to see it here. It's not much else. The Z prime you could see it here. You could eventually also see it in K pi blue bar, but it's more suppressed because you have to pay too light generator. While here the prediction is clean. And there is a very nice connection between these two.
It's very important to have semi-electronics because you have to have a current quark. What about also leptonic ones? Is some space for leptonic?
For instance, the other things would be really nice is tau to renew. This would be super nice again if there's a Z prime. This you expect it. And again, say present bound are not a problem, but by a factor of 1 or 2 orders of magnitude, you should see it out of the moon. It's more difficult because we know much less about the mixing in the electronic sector. So these are nice, especially because here really the leptons are completely of the third generation. So I don't have to make hypotheses about the mixing in the lepton sector. This is why here it can be more precise. Because really third generation, so I don't have to invoke angles which I don't know. Here it's more complicated because the tau mu depends on the Yukawa coupling of the leptons, which I only know the eigenvalue, not the mixing. Okay. So that is why it's more difficult to make prediction. But this is also for quark is easy to make prediction, but then in it's more difficult to see it in B physics because of hadronic uncertainty. This is why these are nice. There, I mean, clearly this I would like to see it there.
More questions?
I have another naive, very naive. But what of all these expectation values and all of these from all these additional gate bosons, for instance, from the point of view of cosmology and density, energy density, and things like that.
This is thanks for the question. So this is if these things make sense, it's fantastic because you have a phase transition, okay, at higher scale, but not too high scale, like QTB. Okay, so potentially here there you have a phase transition related to this spontaneous emission breaking, which for instance could give rise to gravitational wave signal related to the phase transition. Even try to estimate this. Actually, there was very nice work by Admir, Gray, and others who did it also a few years ago. And this would be in the LISA band. So there are a lot of assumptions to do with communication. So we don't make a precise prediction, but it's not impossible that you will see this imprint in gravitational wave. You don't have too much other cosmological implication because I mean all this is related to very early universe. Okay, so you don't have any remnant nowadays, as far as I know.
There is space for more questions.
I have a question, which is some sort of a personal question. You didn't mention supersymmetry. Lectures, you choose what to do, etc. So now, theories never die because. But do you personally think that supersymmetry is still something to investigate? For example, in the FCC, it's supersymmetry something that will be looked on, or is something which didn't work out and doesn't seem to. But this is again, it's a personal opinion.
I think it's a very good question. I think first of all, I think supersymmetry is beautiful, and just because of that, I think it's interesting. And indeed, what has not worked out is really the MSSM. The MSSM really good. But there are other options, and I think in the context of FCC, people have studied. First, I've studied also which will the reach still also in the MSSM or slight extension of the next to email extension. So there are a lot of studies, so we'll continue to be educated. And the only thing I should say is that so from the theoretical point of view, I think supersymmetry is very interesting. For instance, also in this class of theory, at some point, I think you should put in supersymmetry to stabilize. So you can do this symmetry big scale, but then at some point, you really want to stabilize everything. Supersymmetry is perfect, but again, you don't know which scale. From a phenomenological point of view, what I can say is that FCC is a collider for precision physics, right? Which is super sensitive to anything like this contact interaction, but also in the electroweak sector, so not necessary to flavor. So something where you have new three-level effect, or even something that you put in the loop, but with strong coupling in it. Supersymmetry being a weakly interacting theory, okay, the reach is not so high. That is the only thing I can say. It will not be a big breakthrough. FCC, the electron version. FCC HH would be, it's perfect. So I think in these studies which have been done in the preparation of the machine, look at the supersymmetry. Really, the nice things is the HH program of this collider, not too much the electron program. The electron program, the increase in sensitivity for supersymmetry will be something, but not dramatic.
But that is because of the energy scale,
no,
or
because
because
you
of
don't
the...
increase the energy scale.
Yeah, this
You
is the
don't
reason.
increase the energy, you only increase in precision.
That's really...
So you're really sensitive to the Higgs sector, the coupling of the Higgs, and again, supersymmetry, the motivation of the coupling of the Higgs are small. Because Higgs, supersymmetry is a nicely decoupling theory, and you have this loop effect, which are controlled by relatively small couplings, and the effects are not large, because you have produced the parts. If you have supersymmetry with R parity, so you produce all these effects only via loop correction, and these are not particularly large. So there will be some increase in sensitivity, but not dramatic at FCC.
The problem is that you cannot increase the energy with leptons when you accelerate leptons.
So on the other hand, the HH would be perfect to do a order of magnitude improvement in the coverage of.
But the question is more having supersymmetry as an objective or not? And I didn't comment on the comment. Last week, a week ago, I was in Vercelli and Peter Van Nieuwenhuizen was talking. And this somehow was also not really thinking that supersymmetry is available. And he, of course, for him is sort of more difficult to say, but he was saying what we all say, mathematically is beautiful, but there is some sort of not...
basically...
You told me, we believe in what you said for 40 years.
If you have a mathematical beautiful theory, you believe in it. You may say it's never the same from aspect on standard model things. Then things work or don't work. So nature doesn't.
But I think, as I said, probably I think I said it on the first lecture. I think myself and I think also other people have started to be very skeptical about supersymmetry as a solution of the hierarchy problem. This really seems to be difficult. And also the extension not really work.
Which would people study for? And
this was the phenomenological aspect of supersymmetry, why you want to have it at nearby scale. Once you lose this anchor, then can be at any scale.
The breaking is the problem.
That is the problem. So really, that was the anchor to anchor the breaking to the electron.
This another scale, which is a natural. So,
and while other mechanisms, like again, also this I didn't discuss in the lecture, but this composite Higgs idea, which for instance can fit in this picture here, this seems to be more effective to somehow stabilize the Higgs. This is why, for instance, I worked recently on this direction rather than supersymmetry, and until I find the new supersymmetric version which would cure the hierarchy problem. For instance, now that I know our friend Ratats that you mentioned, they work on a mixture of composite Higgs and supersymmetry. So there are still some nice features of supersymmetry that you can
that's cool.
Can I a final comment? It's a bit like SU5. Clearly, you can push scales. The proton doesn't decay, so you can push scales. Now you can do it to symmetry, but somehow the community starts not, young people don't remember, but SU5 seemed to be the unified theories. Then the proton refused to decay. At first seemed that in an Indian gold mine was decayed, but it was not. So now the theory still probably is still alive. You can push scales and stretch, but somehow we.
No, I agree. I see. I think nowadays we have all become much more pragmatic, and I hope, I don't know if I succeed on this, but I mean, all this construction of EFT again, I think are tools. One should have ideas on the UV. The nice thing is that I think there are consistent bottom-up approach which show you that there are classes of extension of the standard model which could have nearby effect. But we need to see this effect, okay? But at least we have a setup where this effect can be there in a consistent way without tuning. I think it's nice. This is what I like. So these things can be at the TV scale, and you can justify why they are at TV scale and why you're not seeing them and why you should see them soon. So this for me is the nice thing. So we should not give up, okay? In terms of course, the hand is the ball is in your hand. In a sense that you should, and you should not be discouraged, okay? Because there are consistent classes. I don't know, because now people say, yeah, this is the desert and nothing. This is dramatic because if it's like this, then you will give up. And I think thinking that there is only the desert was was maybe just given a pessimism of some too optimistic prediction also on the too restricted class of models. So I think I don't share this pessimism. I think that is option. They are consistent, interesting option. Maybe people criticize, for instance, these. I don't think they got too baroque, but again, remember the standard model was also very baroque when it was proposed. People didn't be so. How things is baroque or not baroque will depend only a posteriori you will understand.
Even Kepler was very baroque. They didn't know anything about this bizarre ellipse. Everything in circle.
So there are no reason to give up, many to keep up with the efforts, and there is space for
no, just since we are going to give this talk on Wednesday, if you should say what are the silver bullet of FCC. So there is 1, 2, so that you can sell. How can you sell it? Yes.
I think what FCC what is really outstanding is the potential in the electronic. Okay, the electronic observable will do left in a few minutes. So then you will have the increase in statistics in Z boson is 10 to the 5. So I think we have never seen an increase of statistics. No, in for example, physics. Now there was Argus and there was what was Clio. Each time was basically a factor of 10. In some cases, maybe a bit more, maybe a factor of 100. I'm not sure. Now we see a factor of 10 to the 5. The factor of 10 to the 5 in precision is in statistics, okay, which means a order magnitude in precision. This is really striking. Okay, let me give you why this really opens up something. Okay. You see, if you have, for instance, I like this here, third generation. If you have third generation things, okay, this is suppressed by some scale. So if you compare it to the standard model, you have to pay a suppression factor here. Okay? If you want to see the lateral representation, you have to close the loop and, for instance, see it in Z. So you have this suppression factor, which is roughly speaking this, times the loop suppression factor, which is. Okay. If you look, this is very small, but actually left was only the type of improvement in precision is such that you will be able to see this type of effect. Okay, I don't know if you're being too fast on that. So previously, left was not sensitive to this unless this scale was the electron scale. So it was sensitive to roughly one loop correction, but not loop correction further suppressed by the TV scale. Now we know that there is nothing around the corner, but if there is something at TV scale, the loop effect with this improvement of precision, you will see it. You will see it if you will believe your experiment at 10 to minus 5 precision, which is tough. So that is your problem. But, but if one can believe this experiment at precision, okay, 10 to minus 4. So then we really open up, we really have a threshold, okay? Because we are sensing to one loop effect with heavy new physics. Previously, left was sensitive to one loop effect with light new physics like the top. Top was the light new physics for left, right? You couldn't be sensitive to something much heavier than the top. Now you can. So that is why it's nice.
Nominally gain that loop factor.
Exactly.
That one of
you
60
gain the loop factor, which is all these other factors which are very similar. So it's really breakthrough. You really via electroweak you'll be sensitive to QTB, which is striking.
Other question for comment? Okay. You have no? Not Giampiero. Giampiero. So Giampiero. We close the questions and we
Just,
you can you have a question also.
Greetings to the audience. Yes.
You want to close?
Yes.
Yes. Go.
You can say
Some
in
closing
English.
remarks. So let's thank Gino.
At the end of this lecture,